All right, let's get started here. So our next topic is going to be this chapter on electrochemistry. Electrochemistry is when we have a chemical process that results in the movement of electrons. All right, and our big focus in this chapter are going to be batteries. And so we're going to study these reactions that power batteries. Okay, and these reactions fall into this class of reactions we talked about last semester when we were discussing just classes of reactions, redox reactions. All right, redox reactions are reactions where electrons are being exchanged between two elements. All right, let's say from one element to another. From one, they're going to be, we're going to see they're going to be a different character on the periodic table, and that's what's going to cause the electrons to want to move from one to the other. All right, and this term redox reactions are because every time you have a redox reaction, there's one element that's being oxidized. All right, so this term oxidation, this refers to losing an electron. All right, well, where is that electron going to go? The other element is getting reduced, or the process of reduction is gaining an electron. All right, we're going to throw these terms around quite a bit, so it's really helpful to keep them straight. We have this acronym that we use to help us remember this: oil rig. All right, oil rig. The oil stands for oxidation, is losing. All right, that's how we get our acronym OIL. And then reduction is gaining. Okay, so we just kind of use this, oil rig, not oil rick. All right, this is how we keep this sort of two processes separate in our minds, making sure we keep track of what's what, oxidation being the losing of electrons, reduction being the gaining of electrons. All right, so let's take a look at one. Actually, give me a second. I don't want this to be too busy here. All right, my bad. Pause for dramatic effect. Yeah, sorry. My slides were all uncovered here. Need to cover them back up. All right, my bad. Okay, so we're going to take a look at a redox reaction, one that you may have seen done in the lab, and that is the reaction between zinc and copper. All right, specifically zinc metal. So that's what we have in our beaker here, is this strip of zinc metal, and then copper 2 ions. So we have our zinc metal again, and our copper 2. The sulfate part doesn't even really matter. We just care about those copper 2 ions that are in this solution. Okay? So let's take a look at our chemical equation here. What's going to happen is our zinc is going to go from being this neutral zinc metal to now being these positively charged zinc ions. So in order to do that, did zinc have to lose electrons or gain electrons? Would have to lose them, right? Because those electrons are negatively charged. And is that process of losing electrons oxidation or reduction? Oxidation. Cool. So we have this oxidation of zinc where it's losing those 2 electrons. Well, electrons can't just vanish into thin air. They got to go somewhere, right? So that's what our copper ion is doing here. Notice that copper goes from being this positively charged ion to having a neutral charge, or just being our copper atom. So whereas our zinc is being oxidized, the copper is being reduced, and it's gaining those 2 electrons. Right? That's how it goes from being a positive 2 charge to being neutral. And I'm going to tell you this reaction does indeed occur, right? This is a spontaneous redox reaction here. So if we put this strip of zinc into our solution of copper, what we would observe is all of this sort of dark deposit on that strip of copper, or I'm sorry, on that strip of zinc. All right, these are our new copper atoms. What you can't really see, it's kind of obscured by this picture here, is what's happening to that strip of zinc. Remember, this zinc is going from being these zinc atoms that are neutral to being aqueous zinc ions. So they're being ejected out into that solution where they're floating around. And so now our strip of zinc would actually sort of be deteriorating in this solution here. You would see it getting chewed up by those copper ions. All right, not only that, we can notice what happens to this dark blue color. Again, the dark blue color is a result of those copper ions. And if we compare the color on the left to the color on the right, we can see that our solution's getting lighter and lighter as this reaction's going on, because again, those copper ions, they went from being in solution, floating around, to now being deposited as solid copper. If we were to sort of look, hop into our magic school bus and shrink on down to the molecular level, what we would see is that our copper ions collide with that zinc and they steal those electrons from it. All right, our copper is being reduced. It's gaining those electrons. Those electrons came from those zinc atoms. So the electrons are being stolen from the zinc atom to those copper ions. All right. And so importantly, when those zinc atoms lose those electrons, they now become aqueous zinc ions. So now they're what's floating around in this solution. And our copper atoms start to solidify in that. Again, that's that dark color here in our picture. All right. So what happens is we have this zinc atom. Let me draw a little diagram here. Here's my zinc. And when it starts out, it's got these 2 electrons, right? These 2 valence electrons zipping around here. And of course, this zinc is holding on to those electrons. That's why they don't just go flying out into thin air. Zinc is holding on to these electrons. But as soon as that copper ion approaches, that copper ion is able to pull those electrons away from that zinc atom onto itself. All right, so copper is a little bit of a bully in this situation here. It's stronger and it comes in and it pulls those electrons away from that zinc atom. Okay? We're going to use this terminology a lot, potential. All right, potential is the strength of pull on those electrons. Right? So why does this reaction occur? Why is copper able to wrestle those electrons away from that zinc? Well, because copper has a greater potential than zinc. All right, and chemistry is a real dog-eat-dog world. The strong will win, right? Whoever's got the stronger pull of electrons, whoever's got the greater potential is the one that's going to win, the one that's going to be able to wrestle them away from the other one. All right, so since copper's got its greater potential, it's able to pull those electrons away from those zincs, and that's why we get our spontaneous reaction here where our copper goes from being a copper ion to solid copper atoms, goes from having that +2 charge to being neutral, and the exact opposite happens for zinc. Zinc loses its electrons. It goes from being neutral to having that +2 charge. All right, so we got this idea of this strength of pull of these electrons, this potential. Copper just has a greater potential than zinc, so it's going to win. It's going to pull the electrons onto itself. Cool. All right, so we're going to pause here and we're going to take a look at a battery now. A very, very simple battery. What's called a voltaic cell. We hear this term cell a lot in chemistry. We mean a battery. All right, so let's take a look at our battery here. We have these 2 beakers, and there's 2 hunks of metal sitting in each one of these beakers. And those hunks of metal are connected by this wire. All right, so importantly, in one of these beakers is where we have our zinc ions. So we have this aqueous solution of zinc nitrate. The nitrate's not actually doing anything for us. So let's just go ahead and note that importantly in this solution here are these zinc ions. All right, and that strip of metal that's sitting in that solution of zinc ions is just a hunk of zinc. Right, solid zinc. In our other chamber, we have this solution of copper ions. Again, copper nitrate. We just use nitrates because they're nice and soluble. So really the important thing here is our copper ions. All right, and again, we have this chunk of metal sitting in that solution of copper ions. What is that chunk of metal? That's just solid copper. All right, now, remember what we said is that this reaction here is a spontaneous reaction where zinc will lose its electrons and copper will gain those electrons. And that kind of makes sense when we imagine going back to kinetics in our collision theory. Copper ion collides with the zinc atom and steals its electrons, right, through that collision. Well, it turns out that this potential that exists even when they're in these two separate beakers here. Copper is still able to steal electrons from zinc. It's just going to pull those electrons through this wire, right? So that potential that exists between those two atoms, it exists when they collide together, yes, but it even exists when they're physically separated as long as you give a path for those electrons to cross through. In this case, that wire, right? So those electrons are still going to be pulled away from that zinc atom onto those copper ions. So in one half of our battery here, in one of these chambers, we have our oxidation half reaction occurring. We have our zinc losing electrons. Where do those electrons go? Again, they're going to make their way through this wire to our other terminal of our battery, where our reduction half reaction takes place. Okay, so again, a battery is really just a redox reaction, but where you have these two chambers physically separated. In one chamber, you have your oxidation reaction happening, where those electrons are being lost. Those electrons then travel through a wire to the other half of your battery, where the reduction reaction is taking place, where they're being gained by, in this case, those copper ions. All right? If we wanted to imagine what's happening here in our solution, again, we hop into our magic school bus and shrink on down. Those zinc are again losing electrons, but those electrons are now just traveling up through this piece of zinc metal, through the wire, down to the other end of our battery here. We still have zinc atoms being converted into zinc ions. So what's going to happen to this strip of metal as our battery runs, as this reaction occurs? It's going to dissolve, right? So we're going to start losing zinc atoms as they become zinc ions. So yes, we're going to lose mass over here. All right, and if we hop into our magic school bus and look what happens onto the other side. Well, now those electrons have made their way through that wire down, and we see our copper ions accepting those electrons. And so we're going to get these copper atoms deposited onto our strip of copper over here. So what's going to happen to this end of our battery? It's going to gain mass. And we see that this is why a battery isn't going to be good forever, right? This reaction won't just occur and occur forever and ever and ever, because eventually all of your zinc is going to be consumed and all of your copper ions will have been deposited onto this strip here. All right, we got some battery-specific terminology here. The electrons, what are the electrons are going to be attracted to which end? The positive end or the negative end? The positive end, because electrons are negatively charged, right? So we call this end of the battery the positive end. We call that the cathode. All right, that's where our electrons are traveling to.
Is that just referring to the copper strip or the whole side, the whole thing?
That end of the battery. So the whole this whole operation over here is your cathode. All right, the other end of our battery is the negative end, so that's where electrons start, and that is referred to as the anode. Okay, so importantly, let's kind of summarize here. All right, what's going on in our battery is that copper is again pulling those electrons from that zinc, just like we saw before. But the crazy thing is that this is happening through that wire, right? That potential exists even though these two are physically separated in space. All right. Again, we got some terminology we want to hammer out. We said that oxidation, that was losing electrons. Well, that happens at the negative end of our battery, the anode. All right, so we're just going to note oxidation at that negative anode. And our other half reaction, the reduction, at that positive cathode. All right, and so our electrons will flow from anode to cathode. It is not the exact same as electronegativity. It is also not completely separate. We're going to see that elements that have a large electronegativity also tend to have high potential. But copper and zinc, for example, have very similar electronegativities, and yet they have different potentials associated with them. So they are not one and the same, although they are somewhat related. You know, they're cousins, let's say.
Is there a trend potential, or how do we determine?
That's a great question, and we're going to see a big old chart where we're going to see all elements potentials and stuff like that.
Okay.
Yep. Cool. All right, so just to make note here, right, we have our oxidation state. Let's see, how are we going to keep these straight? Let's kind of try to figure this out here. Well, again, the negative end is the anode, and the positive end is the cathode. Does this sound familiar to anybody about anything? Cations and anions, right? So anions were negatively charged ions. Cations were positively charged ions. So we see that same kind of recycling of terminology. All right. We want to remember that oxidation takes place at the anode and reduction takes place at the cathode. All right. This is not the greatest way to do this, but for me, I remember this because both oxidation and anodes start with vowels, and reduction and cathode both start with consonants. I don't know, I'm a weird alphabet guy sometimes. Sometimes that stuff helps. All right, so oxidation takes place at the negative end of our battery, our anode. Reduction takes place at the positive end of our battery, the cathode. And again, electrons will flow from anode to cathode. Cool. All right, so again, our electrons are going to flow from anode to cathode. So then why is this useful for us human beings? Well, if all you did was put a wire in between there, great, you would allow this battery to go. But really what we like to do is we stick some sort of resistance source there, like a light bulb or an electronic or whatever it may be, to take advantage of that flow of electricity, right? That's why we use batteries. So when you stick that AA battery into your remote control, you got to line it up in such a way, right, so that there's a positive end and a negative end. Well, what's happening is electrons are being released from that negative end. They're flowing through that remote control, powering that remote control, and going then to the other end of the battery. All right, so in the middle of this wire here, we stick some electronic that we care to power. All right, there's one other aspect of this battery that I've glossed over up until now, and that is what the heck is going on in the middle here. Okay, this is an important piece of every battery because if we look at what's happening in our anode here, we have zinc atoms becoming zinc ions, right? So as this reaction is going, our beaker starts to fill up with a whole bunch of positively charged zinc ions. All right, and nature hates a charge imbalance. Not only that, but if we look at the other end of our battery, what's happening is our copper ions that used to be floating around in solution are now becoming neutral copper atoms. So we had all these copper ions in here, and as this reaction occurs, we're losing them. They're becoming deposited as neutral atoms onto this strip. And again, nature hates a charge imbalance, right? So in one beaker, we're generating a lot of positive charge over here in our anode. And in our other beaker, we're consuming a lot of positive charge. So this middle bit right here is what's called the salt bridge. Your salt bridge contains some sort of soluble salt, in this case potassium nitrate. And what happens is, as this reaction occurs, we'll have negatively charged nitrate ions flowing into our anode in order to keep everything charge balanced. And we'll have positively charged potassium ions flowing into our cathode to keep everything charge balanced. All right, so we have this salt bridge in the middle here. The claim to fame of your salt bridge is that it keeps both of the ends of your battery, what we call terminals, charge balanced. Yeah, they're just like glass wool or whatever. They make it so it doesn't mix really quickly. You don't just dump the two together, but you have a channel where these ions can pass through. All right, so this is our very simple battery, one that we can make in the lab here. Again, it's powered by this redox reaction. We have oxidation at one end. Those electrons are being released and travel to the other end where our reduction reaction is taking place. And I know everybody's like, look, I've seen a battery before, and it's not two beakers, all right? Duh, I agree. But all batteries do have these same two chambers in them. Yes, we've gotten very clever with our engineering and packaged them together in these really small things. But if you crack open that AA battery inside your remote control, you will indeed find two chambers. One where there's an oxidation reaction taking place, and one where there's a reduction reaction taking place. And those two chambers are separated until you connect them with this wire here that allows the electrons to flow from one to the other, right? And that's eventually why, you store your battery for a long time and it stays good. As soon as you put it in that remote control, it's got a limited lifespan, right? Because now all of a sudden you've kicked off this redox reaction, all right? We'll take a look at some real batteries and kind of how they're designed, but this is kind of the simplest one that illustrates all these important parts here. Cool. All right. Another thing that so first thing, anatomy of a battery, check. Now we're going to learn how to turn this battery contents into what we call standard cell notation. All right, this is this shorthand to summarize a battery's contents. All right, so I'm going to copy over these two half reactions here. Oops. Okay, so what we're going to do is we're going to list our anode material followed by that anode solution. All right, what is it that makes up that solid piece of our anode? That is our zinc metal. and our anode solution are those zinc ions. All right, so in our standard cell notation here, the first thing is that anode material, zinc, solid, and then we use this vertical bar to separate our anode solution, our aqueous zinc ions. All right, and then we're going to have these two vertical bars. And they're going to separate what happens at the cathode. We're going to first list our cathode solution, followed by our cathode material. All right, so in our cathode solution, we have our aqueous copper ions. Again, we're going to have this vertical bar separating our cathode solution from our cathode material. And our cathode was made out of that solid copper. All right, so this right here we would say is the summary of our battery's contents in, again, what we call standard cell notation. Tells you all the important bits that are included in your battery. What's going on at the anode? What's the solid material the electrons are going to pass through? And what's in the solution? And what's going on at your cathode? What's in the solution? And what's the solid piece of material those electrons are going to pass through? Okay, so now we want to start talking about batteries quantitatively, but first we're going to have to introduce some units here. All right, some of these may be familiar with those who have taken any sort of electricity and magnetism, I believe is the course in physics. Others, these might be new units, but these are units that we use to talk about electricity and stuff like that. All right, so the first is what we call the coulomb. And we use capital C. All right, a coulomb is used to measure charge. All right, we talk about charge a lot, +1, -1, all that sort of stuff. Well, if you want to go in and measure charge in a sample, you got to have units, right? The units that you use are the coulomb. All right, the next is an ampere or an amp. An amp is used to measure what's called current. Which is the flow of electrons. All right, an amp by definition. I'm going to use these fancy three-pronged equal sign here to indicate this is how it's defined. Is a coulomb per second. All right, and the last one, arguably the most important one for this topic, are volts, capital V. right? A volt is the unit that we use to measure potential. All right, and remember what we said about potential, what's kind of the easy way to think about potential. This is the strength of pull on electrons. From anode to cathode, exactly. All right, and a volt is defined in units of joules per coulomb. Right? So by strength of that pull, we really mean the energy pulling those electrons. Cool. So what makes a different battery going on? Like what if I used one redox reaction over another? We would find that we have a different potential. So how do we calculate what we're going to call standard potential in our battery? All right, so importantly, this is going to use our constants page for this chapter. All right, let's just sort of take a zoom out here. What we see here are a whole bunch of reduction half reactions. All right, so let's just take a look at our familiar one of our copper 2 ion. I just had it. Oh, here it is. Our copper 2 ion accepting those 2 electrons and becoming solid copper. Right? This was our reduction reaction in our example battery. And we see that there's this value associated with it here. All right? This is what we call our standard potential, our reduction potential, or just potential. Okay, so copper has this reduction potential of 0.34 volts. And remember, we said that copper was stronger than zinc. That's why that reaction proceeded spontaneously. So let's find our zinc reaction on here. All right, we see that zinc's reduction potential is indeed less, that 0.76 value. So again, copper having that larger reduction potential, that's the same way as saying copper's stronger at pulling electrons. All right? In fact, our entire list here is this ordered list. We can see up at the very top we have our highest reduction potential versus down at the bottom our lowest reduction potential. All right, if we want to zoom in on that top reaction, that is indeed our most electronegative element, fluorine. Very good at pulling electrons, right? So fluorine's reduction potential is the highest up here, that 2.87 volts. If we go to the opposite end, these are the things that suck at pulling electrons, right? So these are our group 1 ions, like lithium and potassium. Sodium's up here, right? We know those group 1 metals and group 2 metals, they like forming positively charged ions because they don't hold on to their electrons very strongly. So they're actually terrible as far as reduction potential goes, right? So we got this ordered list here of all these different half reactions in order of their reduction potential. Okay? Cool. So in this reaction, we said that copper was going to be reduced. Check, check. That's this one here. But our zinc wasn't being reduced, it was being oxidized. So how am I supposed to figure out where that reaction is on this chart? Well, importantly, this chart is only listing reduction reactions. So where do I look for my oxidation reactions? It would just be going the opposite way, exactly. Right? So these oxidation half reactions are the reverse of those reduction half reactions. All right, so since it's going to be the reverse of it, how do I calculate the potential of this battery? All right, we have a very simple equation here. The standard potential, E naught, of our battery, our cell, is equal to the standard potential at the cathode minus the standard potential at the anode. And remember, your cathode is where reduction happens. Your anode is where the oxidation happens. All right, so everybody take a second using this formula here, and I'll go back to our constants page. Let's make note of these values. All right. Calculate the standard potential of our battery. All right, being good with my units here, we have our 0.34 volts minus our negative 0.76 volts. So the standard potential of this battery is 1.1, and I'm going to be good with my sig figs. I need 2 decimal places because this is a subtraction problem. 1.10 volts. All right, we have this very simple equation here, and one thing that I just want to point out is that we don't have any stoichiometric coefficients that appear in this equation. Stoichiometric coefficients do not factor in to potential. All right, so why is that? Because if we go back to our definition of our potential, our volts, a volt is the joule per coulomb, right? Which is the charge of our electrons here. So we can think about our volt as the amount of energy per our electron charge. All right, and since each electron's got the same charge associated with it, it's not like one's going to be different than the other. Okay, so going back to our table here, so for example, in this one here, that 0.34 volts, that is what each one of those two electrons is feeling the pull of. Right, the energy per coulomb. Cool. All right, so we got some terminology here. When E naught of our cell is greater than 0, we say that that is a spontaneous battery. All right, when E naught cell is less than 0, we would say that that is a non-spontaneous battery. All right, but remember, if it was non-spontaneous, that simply meant it was spontaneous in the reverse direction. All right, which in the world of batteries quite simply means that you swapped your anode and your cathode. Your electrons are flowing the opposite direction of the way that you thought, right? The reaction's actually going the other direction in terms of our flow of electrons. All right, so we have this constants page that will help us calculate our standard potential of our battery. We take our cathode potential minus our anode potential. All right, this is measured in volts. We don't see any stoichiometric coefficients that appear in that equation. And we have that if our potential is greater than 0, that's a spontaneous battery. And if that potential is less than 0, that's a non-spontaneous battery. And this terminology, spontaneous, non-spontaneous, everybody's like, oh, I've heard of that before. When did we talk about this? Thermodynamics, and with respect to which one of those three variables? Gibbs free energy, yes, delta G, absolutely. Okay, and there is a direct relationship between our standard potential and our Gibbs free energy. All right, so what we're going to do is we're going to derive this relationship here. We want delta G naught to be equal to E naught cell, and then we're going to have to add some stuff over here as well to make sure that they're equal to one another. All right, so the first thing we're going to have to do is worry about the sign. For my E naught cell, I said that a positive value was spontaneous. For delta G, what is it, positive or negative? Negative spontaneous. So in our equation here, we're going to have to pick, or rather introduce, this negative sign. All right. Lastly, we got a units problem here, because if we remember, delta G is measured in kilojoules per mole. All right, but importantly, per mole what? So it's actually a mole reaction. which is when you draw your balanced chemical equation, you're saying what a mole of reaction is, right? So that's defined by your balanced chemical equation. When one of your reactions happen as written, that's a mole of reaction. All right, and we know that our E naught cell is in joules per coulomb. And we can get from joules to kilojoules pretty easily, but we got a problem with our denominator here. Coulombs and moles reaction are not the same. All right? So what we're going to do is we're going to multiply the right-hand side here by what's called Faraday's constant. Because Faraday's constant tells us how many coulombs there are, the charge, of 1 mole of electrons. All right, again, a coulomb is our unit for measuring charge. If we had 1 mole of electrons, what would the charge be? That's Faraday's constant. All right, and we're almost there. We have moles electron, moles of reaction, so we're going to multiply by one more term here, N. All right, this is the number of electrons exchanged in your reaction. So our units would be moles of electron per mole reaction. If we stick a joule to kilojoule unit conversion on there, we see that now both sides are equal to one another in terms of units. All right, so we're just going to kind of rearrange this equation a little bit to fit how it looks in our textbook. Delta G equals negative NF E naught cell. All right, Faraday's constant is just a constant. If we look at our constants page for this course, it's one of them over here. Four 484.6. All right, so Faraday's constant is 46484.6. And again, this is coulombs per mole electron. Okay, so then for our reaction, let's go ahead and calculate our delta G naught here. All right, but what is that number going to be for N in our reaction? Let's take a careful look at our half reactions. How many electrons are being exchanged in our particular reaction here? 2 of them. So we need to pay attention to our balanced redox equation in order to find out how many electrons are being exchanged. All right, notice how that didn't appear anywhere in our potential formula. All right, because again, our units were in joules per coulomb. Right, that was the amount of energy each electron was feeling. But it's going to appear in our delta G formula here. This is 2 moles of electrons per mole reaction. All right, times Faraday's 46484.6 coulombs per mole electron times our potential, our 1.10 volts. All right, if we punch this into the calculator as is, I'm going to do 3 sig figs here. I get 212,000. All right, well, why would that be? My moles of electrons cancel out. All right, but we got to remember our volt is a joule per coulomb. Now coulombs cancel out. So this is joules per mole reaction. And as we said, we like to look at delta G instead of kilojoules per mole reaction. So we can divide by 1,000 here to get our 212 kilojoules per mole reaction. All right, so here I just inserted that definition of a volt to look at my units. And I see that if I just use this equation as is, I'm left with joules per mole reaction. I can divide by 1,000 to get to my kilojoules per mole reaction. And we get a large negative delta G here. So we see that this is indeed what we would say is a spontaneous reaction. What's up?
How did you get 212?
I took my 212,000 and I divided it by 1,000. Negative 212.
Negative 2 times 46.4.6 is times 1.1 is negative.
Yeah, hold up. What did I do wrong? It's not 46. I read this number wrong. It's 96. Yeah, my bad. I was looking at it like, wow, that's a lot more 4s than I remember, but okay. Yes, 96,484.6. Thank you.
I was sitting here like, this is about half the number you have.
Yeah, awesome. Good catch. So when we use our real Faraday's constant, we see that we get our negative 212 kilojoules per mole. Cool. All right, so we have our redox reactions. If we take those redox reactions and we physically separate them into 2 chambers, as long as we connect that chamber by a wire, those electrons have a path to flow through, and that's how we create a battery. All right, we can summarize the contents of a battery in this standard cell notation, where we summarize our anode material in solution, as well as our cathode material in solution. We can calculate how strong that battery is, how strong the electrons are being pulled from one end to the other by calculating the standard potential. There's very simple cathode minus anode equation here. There's a relationship between our delta G and our standard potential that will allow us to calculate the free energy of that battery as well. Cool. All right, let's repeat this process here, but we're going to look at a new battery here, and I want you all to give me these pieces of information. All right, so first of all, here's this battery. All right, on the one end, I have an iron ion solution. And in that solution is sitting this hunk of iron metal. All right, given that the electrons are flowing away from the iron into the other beaker, which one's my anode and which one's my cathode, the left or the right? So my anode is going to be where those electrons start, the negative end of that battery. The cathode is going to be where those electrons flow to, the positive end of my battery. All right, so our oxidation reaction that's taking place at that anode is my solid iron losing 2 electrons to become the iron 2 ion. All right, my other reaction taking place, my reduction reaction, is a permanganate ion in acidic conditions, gaining 5 electrons to become a manganese 2 ion. All right? But now let's look carefully here. What are we going to make our cathode out of? All right, over here it was simple enough. Iron was involved in our reaction. Yeah, let's make that anode made out of iron metal. If we look at our reduction reaction, what we're going to note is that there are no solids in this reaction. Everything is aqueous. So then what the heck are we supposed to make our cathode out of? Well, importantly, all that hunk of metal in that solution is really doing is help delivering the electrons from the anode into that solution so that they can react with those permanganate ions. So it doesn't actually need to be a participant in the reaction. So in this case, where we have all aqueous components in our balanced chemical equation, or rather in our half reaction, we're going to use an inert metal as our terminal material. All right, and there are a few different metals that you could use, but for the sake of simplicity, we're always going to default to what is the best one, platinum. All right, so platinum is a nice inert metal. Its only job in life is to play like handoff of electrons. All right, and so that's what it's going to be doing here in our solution. All right, so step one, let's take this battery and summarize its contents into that standard cell notation. All right, so given our battery here, everybody take a second, see if you can't put the contents of this battery into that standard cell notation. You don't have to include water. No, you do have to include all the aqueous, but not the water.
So anytime there's like a liquid, you just don't include it?
If it's water.
Okay.
If it was like bromine or something like that, that would be an important component of the battery. But we assume water is present.
Okay.
Those are the only two examples I could think of a liquid being in there. But all right, so our anode is going to be made out of that solid piece of iron. Our anode solution are those iron 2 ions. All right, but now we got a bunch going on in this cathode solution here. So I'm going to make a little bit more room. Oops. All right, we have that permanganate ion. And to be clear, what you are going to include is everything other than your water, because again, we can assume that water is present. All right, what you also don't have to include is any balancing coefficients. So it's just a list of these compounds in there. Your permanganate, your hydrogen ions, we do want to indicate that we have acidic conditions. And our manganese 2 ions are also floating around in that solution. And so then what is our cathode material in this special case? Because we have all these aqueous. That inert platinum, yep. So just PT solid. Cool, so now that we got that battery summarized here in standard cell notation, let's go ahead and calculate our standard potential. All right, I'm going to bring up that constants page. I'm pretty sure these are like on opposite ends here, so I'm going to go ahead and copy and paste onto that other page. All right, and just to note, you do got to be careful, right? So permanganate, we have 2 different reduction reactions that can take place for permanganate ions. We need to make sure to grab our half reaction exactly, so exact matches here. All right, so here's one. Same thing with the other one. We got a bunch of irons going on. Here's iron 3 up here. Iron 2 down here. We want to make sure to grab the iron 2 entry. Cool, so here's our 2 entries from, I just hunted those down, right, and pulled them from our constants page. Everybody take a second and calculate our standard potential. All right, so as we noted up here, our cathode is that permanganate solution. So here's my reduction reaction taking place at that cathode minus my negative 0.45 volts from my oxidation half reaction. Remember, that's looking in this direction here, the opposite. So we get a standard cell potential of 1.96 volts. All right, so compared to our zinc copper battery, this battery here, those electrons are being pulled with a much greater energy from one end to the other, which this isn't really a circuitry class or anything like that, but why you would care is because of what you stick in the middle here, right? So what you stick in the middle provides what's called resistance, and so some things need a greater voltage than others, whatever. Well, you can cover that in physics. All right. We'll just note here that we get a greater potential for this particular battery because of our redox reaction that's powering it. All right, so next we want to calculate our free energy. All right, but before we do that, because I imagine there's going to be one common pitfall, I want everybody to take a second and first give me the balanced chemical equation for this redox reaction. We have these two half reactions, but we've never actually given our balanced chemical equation yet. All right, so I got my reduction half reaction. I got my oxidation half reaction where I took that reaction from my chart and I flipped it, right? So that we have electrons being lost in that oxidation reaction. And now I want to sum these up into my overall chemical equation. All right, but what's that last step that we need to worry about before we can sum these up? We need to cancel our electrons, right? Yeah, so we need the electrons to be the same on both sides. I have 5 over here and 2 over here. I can't turn a 2 into a 5, so I'm going to turn them both into that. Least common multiple. Multiply this one by 2. Multiple this one by 5. All right, so I'm going to multiply everything in that top reaction by 2. So now I have 2 permanganates, 16 protons, and 10 electrons, combining with these 5 iron atoms. So give me 2 manganese ions, 8 waters, five iron ions, and those 10 electrons. All right, and again, we did that so that we could cross out our electrons from both sides.
Well, we use that 10 for our end line.
Correct, exactly. So now we're going to do the last step here, which is to calculate our free energy. All right, so everybody take a second and calculate that delta G naught. I lied. We'll do it together because we're running out of time. And exactly, the reason why we wanted to make sure to balance that chemical equation first is because that value of N in our equation for delta G is going to equal those 10 electrons that are being exchanged in this reaction. All right, so we get this gigantic value. But this is joules per mole reaction. All right, so we can convert this to kilojoules per mole reaction. It's still a pretty massive number. But yes, negative 1891 kilojoules per mole. Cool. All right, so given that battery, we can figure out how to summarize its contents in that standard cell notation. We can calculate the standard potential by taking the potential at the cathode minus the anode. And then once we have our balanced chemical equation and we know how many electrons are being exchanged in our redox reaction, we can calculate the free energy change of that reaction. Cool. All right, we're going to leave it there. We will pick up with this next time. I ran 5 minutes over. We'll start lab 5 minutes late. Say it again? No, unfortunately not. No. You do get one dropped at the end of the semester if for whatever reason you can't make it. Oh, okay. Yeah, unfortunately not. We are too close to the end of the semester here to book makeup labs. Yeah.